So when dealing with rotational motion, we're now going to look at the kinematics of rotational motion. Just like before, kinematics just means how does an object move? We don't care about what causes the motion. In linear terms, of course, the motion is caused by forces. In angular terms, the motion is caused by torques. And we'll get into more detail when we talk about the dynamics of rotational motion. But here we're just worried about the kinematics. So I have here a comparison between the translational rotational motion equations we had earlier this semester and the newer rotational kinematic equations your book introduces today. So translational motion dealt with three major issues, right? We had position x, velocity v, acceleration a, and technically we also had time t. Rotational motion has analogs to these. They have angular position, theta, angular velocity, omega, angular acceleration, alpha, and still just plain old time. Time doesn't have an angular component. So we have equations, the average velocity, and remember these kinematics equations were for constant acceleration. So we're not worried about forces at this time. So these are constant acceleration equations, both constant linear acceleration for the translational equations and constant angular acceleration for the rotational equations. So the average velocity was equal to the displacement over time. The average angular velocity is equal to the angular displacement over time. We had the velocity was equal to the initial velocity plus the acceleration times time. Here we have the angular speed is equal to the initial angular speed plus the angular acceleration times time. See how the analogs fit in. V is the linear speed, omega is the angular speed. These equations are identical in form. We're just replacing the translational variables with the rotational ones. That's it. This equation, the long equation, the position is equal to the initial position plus the initial velocity times time plus 1/2 the acceleration times time squared. One of our constant acceleration equations. It has a rotational analog. Instead of x, we have the position, angular position. Instead of the initial linear position, we have the initial angular position. Instead of the linear velocity, initially we have the initial angular velocity. Time is still time. 1/2 the linear acceleration plus 1/2 here the angular acceleration. Time is squared here, time is squared here. So you can see how the equations are identical in form. And then given the other two equations we have, linear speed squared is equal to the initial speed squared plus 2a delta x. Angular speed squared is equal to the initial angular speed squared plus 2 alpha delta theta. And finally, linear velocity, assuming constant acceleration, the average linear velocity is just the initial plus the final over 2. That's what average means. Take two numbers, add them together, and divide by 2. And here we have the angular version of that. Again, assuming constant acceleration. So the problems you're going to be solving are very, very similar in form to what you have already solved in the earlier kinematics chapters. But now we're just dealing with angular rotation. So an object might start from rest and then rotate up through some speed. So imagine a bicycle wheel starting at a stop sign, and as you pedal, the wheel gets faster and faster. Well, since it starts at rest, the angular speed, initial angular speed, would be 0. If you know what the angular acceleration is, you know how much time has elapsed, you can tell me what the angular speed is at some later time. So look to these worked out example problems to solve these rotational kinematics equations. And they're set up very much the same way as you set up the earlier translational kinematics equations. And when we move to dynamics, you'll also see a connection between the linear equations we've already dealt with, kinetic energy, momentum, and so on, compared to the angular versions of those energies and momenta.